Welcome to 1007 ICT, 1807 ICT, and 7611 ICT. We're looking now at the revision lecture, and so before we start the revision lecture, just talk about a little bit of the idea, I guess, for this session. It will review the content that was covered in the course. It will focus mainly on the process-based questions. There can be other kinds of questions like definitions and so on, and short answer questions. So they're certainly going to be in the exam in some sense, but for this particular session, we're going to look at the things where we actually work stuff out. Coverage of specific topics in this session or lack thereof does not in any way imply that those topics will or will not feature on the exam. Okay, all content is accessible and should be revised. You'll get a recording of this session. You are not allowed calculators or anything electronic in the exam. So that should give you an indication about some of the kinds of questions we can ask you, because some may require a calculator. But having said that, there are examples of questions that you think might need a calculator that actually don't need one because of just the nature of the numbers. Before we go on here, I would really appreciate it if you would complete the online course in teaching about valuations for the course. You can do that through the Experience at Griffith link in the Griffith portal. You would have got an email about that already, and so please do that. It actually does really help us to improve the course. So, Lecture 1, Part A, Course Overview, that is not accessible. Right, it was basically what's the course about, so I'm not going to ask you questions about that in the exam. I should point out at this point that there are no multiple choice questions on the final exam, right? So it's all either short answer, process based, those kinds of questions. Part B, Introduction to Computers, is accessible, and in that section we looked at, well, what is a computer system? We looked at mechanical, electromechanical, electronic computers, integrated circuits, evolution of computer processors and storage, quantum, optical, nanocomputing, different types of computers, and computer system abstractions. And just looking at the topics here, there really wasn't any kind of process-based stuff that we did here. So it was all really just descriptions of things and understanding and a bit of history and so on. So these would make good short answer questions, like what do we mean by nanocomputing, for example, or those kinds of questions. All right, so you're not typically going to get a process-based question out of this type of content. Lecture 2 is where we start doing some more process-based stuff, and we covered the idea of data representation. So this topic cuts through pretty much everything that we do in the rest of the course. You'll see binary numbers and number representations and so on come up all through the course after this point. So we looked at computer data, and key idea here was that data can be converted to sequences of ones and zeros. So if we want to represent a binary integer, for example, and we have a number here like 177, we want to represent that as binary. Apparently this value here, 10110001, apparently that's 177. How would you verify that that's the case? Well, again, each column has a heading, and the column headings are 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. And 2 to the 0 is 1, 2 to the 2, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So typically, unless we need the powers of 2, we will just count 1, 2, 4, 8, 16, so on. Alright. Sometimes we need the powers of 2, so we need to remember that they're there and what they mean, but mostly it'll just be 1, 2, 4, 8, 16, and so on. So if that's the case, and each column is worth that much, what's the first one worth on the left here? It's worth 128. 64, there's none of them. There is a 32, there is a 16, there's no 8s, there's no 4s, there's no 2s, but there is a 1. If you add those up, 128 plus 32 plus 16 plus 1, you're going to get 150, 60, 176, 177. Okay, so we did a number of things there, and we spent quite a bit more time doing that when we actually did the content, but that's the basic process. The binary representation, every column has a value, and it's a power of 2. Looking at powers in different bases, we have base 10, the one we normally use, which is not actually that useful in a computing environment. So we typically tend to use base 2, base 8, or base 16. And so base 8 is the one we use the least, generally. We use typically base 2 or base 16. And the base 16 is nice and convenient. Every 4 bits, or every 4 bits is 1 digit. So that makes it nice and compact in terms of writing it down. What it does mean is that for hexadecimal, for example, the base 16, we run out of digits, so we need to use A, B, C, D, E, and so on for digits that are 10 and above. When we're looking at the integer word size, so this is another topic in lecture 2, if we have a word size in bits of 1, we have 2 values, and the range is 0 to 1. If I have 2 bits, I can represent 4 different things, and the range is 0 to 3. If I have 3 bits, I can represent 8 things, and the range is 0 to 7. So basically, the values that I can represent, here 2 to the 3 is 8. 2 to the 4 is 16, so 2 to the 5 would be 32. It just doubles each time. So in 5 bits, I can represent 32 things, and the range would be 0 to 31. 1 less than. Okay, so you can keep doing this for all these different values. The general form, though, is with n bits, you can represent 2 to the n values, and the range will be 0 to 2 to the n, and then subtract 1. That's the general form. So it doesn't matter how many bits you have, you can always work out what the value is going to be. That's 2 to the power of that thing, minus 1. When we want to convert, so a lot of the things that we do, we have something in one base and we want to convert it to a different base. So converting things from one way to another is decimal to binary, binary to decimal. We've also seen to octal, right? We've seen a number of different configurations here. So any of those you should be familiar with and able to do. So converting from decimal to binary, if I've got a number like 165, there's an algorithm. Basically, what you do is you find the largest power of 2 that still fits, and then subtract those values. So let's have a look at it. We've got 165. If I look at my powers of 2, I've got 1, 2, 4, 8, 16, 32, 64, 128, 256. So 128 is still smaller than 165. You would agree with that, right? So 256 is too big. So do I need a 256? No. There will not be any 256s in my answer. It's too big. So what's the biggest thing that will be there? It'll be a 128. So 165 minus 128 is... Sorry? $37? Good. Okay, so there's no 64s. There is a 32, which leaves 5, so there's no 16s, no 8s, oh 4, there's 1 left over, no 2, and we should end up with a 0. Yeah, so we've been doing this quite a lot. One of the things you'll find with the exam, you'll be doing a lot of these kind of small number computations, so it's something that probably is useful to practice, to work with. Now you'll find that a lot of the numbers are very similar. You tend to use a lot of 128s and 64s and so on, but you should be able to do these fairly quickly, and you won't have a calculator, right? So there's an alternate for this, and some people prefer this. I find this more work, but you can basically take the number that you have, like 79 in this case, divide it by 2. You get 39, a remainder of 1. 39 divided by 2 is 19, with a remainder of 1. 19 divided by 2 is 9, remainder of 1. 9 divided by 2 is 4, remainder of 1. 4 divided by 2 is 2, no remainder. 2 divided by 2 is no remainder. 1 divided by 2 is 0 and a remainder of 1. It doesn't divide, okay? And then what you do is you take it this way, and so you're going to get 1, 0, 0, 1, 1, 1, 1. 1 too far over. 0, 1, 0, 1, 1, 1, 1. There we go. So this is 79 in binary. As I said, this is, I think it's more work. I prefer the other model, but both of the models work, and you can use either of those to convert from decimal to binary. Hexadecimal and octal, we already talked about these previously. Basically, hexadecimal, 4 bits for every digit. Octal, 3 bits for every digit. So that means the range for hexadecimal is 0 to 15. You don't have digits for 10, 11, 12, 13, 14, and 15, so you're going to have to use letters. And so letter A is 10, letter B is 11, and so on. Octal you don't have that problem with. There's only 3 bits. That means it's 0 through to 7, or 8 values in total. Looking at the next thing that we looked at was binary addition. And so what we're doing is we're going to add two numbers together. First thing you can do, and this is a shortcut, you can work it out in decimal first. Right, you still have to show working, so you're going to have to show how this you came up with this. But basically, if you do the computation in decimal, what's this number here? It's a 128 plus 64 plus an 8 plus a 4 plus a 1. So you add those up, what do you get? 12, 25, 8, 10, 205 it looks like. Plus, and what's this one? 128 plus 8 plus 1, 137. Yep. So 205 plus 137 is 342. And now I can use my algorithm to work out, well, 342. Is there a 1? Yes, 2, 4, all, yep. 128, yes. 256 still fits. 512 would be the next one. Does 512 still fit in 342? No, so there's no 512. There is a 256. Okay, so 256, 342 minus 256. What do we get? $86. Okay, so we have 86. Is there a 128 and 86? No. Is there a 64? Yep, so minus 64, what do we get? 22. So there's no 32, but there is a 16. What do we get? 6. So there's no 8, but there is a 4. This is a 2, and that means there's a 2. And luckily I've run out of room, so there's no 1s. And apparently that's 342. So did I actually do this addition in binary or not? No, I did it in decimal. I can certainly do that. I can still get the right answer as long as I know how to convert things. So this is a shorthand way of doing it. In terms of if a question says you need to show the working, then probably this is not sufficient. Does that make sense? Okay. One thing you can do with this, though, is really easily check your work. So if you think, I'm not really sure if that's the answer, you can verify it with this. So normal binary addition. How does it work? Well, these are the different cases that we have on the right here. Let's just do the addition. 1 plus 1 is 0, carry the 1. 0 plus 0 plus 1 is 1. 1 plus 0 is 1. Sorry. 1 plus 1 is 0, carry the 1. 1, 0, 1, 0, carry the 1. That means we have some leading zeros here, so this becomes a 1. Now, on a piece of paper, you can certainly do this. You can make it stretch. You can go further to the left if you want to. In a computer, you have a limited amount of space. So if something goes to the left of how much space you have, what happens to it? It gets cancelled out, or it falls off the end, basically. It's discarded. And you are left with just the bits that you have space for. So once we did addition, we went on to representing negative numbers. So negative numbers we found were a bit complicated, but they comprised of 3 different ideas actually. One of them was that you need a plus and minus sign. Another one was that you need to complement or flip the bits, and the final thing was you're always out by 1, so you have to add 1 back in to the answer. So the first part here is just illustrating the plus and minus sign. So we use 1 bit for plus and minus, happens to be the leftmost one. That's the most useful one to work with for us. So this number here, 164 plus an 8 is 72, plus a 1 is 73. Because this is a 0, this is plus 73. This one here is the same number, 73, but there's a 1 here, which means this is minus 73. Now, we found in our lectures that just doing this is not enough, right? You don't actually get negative values, negative quantities, so you need more to make the negation work properly. So what we looked at was something called 1's complement. So 1's complement is basically you have the sign bit and you flip the bits. So if I have this number 011001111, what number is this? 64 plus a 32 is 96, plus a 4 is 100, plus 2 is 102, plus 1 is, apparently this is 103. It's positive 103 because there's a 0 there, Yep. And now what I'm going to do is I'm just going to flip these bits. So a 1 becomes a 0 and a 0 becomes a 1. Okay? And so this is apparently minus 103. It doesn't quite work. Yeah? And so we need an extra step. We actually need to add 1 to this to make it work properly. So the plus 1 is still missing. Okay, so again, this is on the way to making the negation work properly, but it's really close. And the reason you can tell that it's really close, if I add these two things together, what am I going to get? All ones. You can see that's really close to 0. If I add 1 to this, I'm going to get back to 0. That 1 will carry all the way across. So you can see where the plus 1 comes from. We're just out by a little bit if we just follow this scheme so far. So 2's complement was the actual mechanism for doing negation, and basically it's the sign bit, 1's complement, and add 1. So to do that, first you've got a number like this, and this is 32 plus 8, which is 40. So we want minus 40. So how do we do that? We take that number 40 and we first of all flip the bits, and then we add 1. And so 1 plus 1 is 0 carry the 1, 0 carry the 1, 0 carry the 1, 1, 1, 0, 1, 1. And apparently this is minus 40. And based on what we saw, that if we combine the plus and minus sign, the complement, flipping the bits, and then adding 1, we will end up with the negative value, the equivalent negative value here. So that's 40, this will be negative 40. This is the long way to do this. There is a shorter way, more convenient. If I have this number, so this is whatever number it is, what I can do is I can find the rightmost one, keep it and everything to the right, and then flip everything to the left. So if I did that, I will have 1, 0, 0, 0, and then if I flip the other side, I get 1, 0, 1, 1. Apparently that is the negative equivalent. Now if that's the case, if I do this again, should I get back to my original number? I should. So I'm going to keep these guys and flip this side. Are those two the same? Yep. Okay. So we can at least verify that you will get the same result. And you can compare this with the 2's complement method and you will get the same result. So this is a shorthand. As long as you remember to find the rightmost one, keep everything to the right of it, including it, and then flip everything to the left. This one's easier to work with, but you do have to remember the rules for doing it. Whereas 2's complement, you can do from first principles. You can just say flip the bits and add 1. It's more work, but maybe it's easier to remember that process. So do you think there are going to be some questions around this type of stuff on the exam? Absolutely, right? It shows up in lots of different places. Character data. We talked about ASCII. This table, ASCII table, it's a little bit different from a lot of other ASCII tables that we've been using in the course. So for example, if I want to find the character G in ASCII, well, where is it? It's capital G, so it's this one. So I need to go this way first. So it's in the 4 column. Right, so it's 4, and it's in the 7 row. So it's 4, 7 in base 16. Yep. Does it have any other values? Well, it could be 0100 and 011. Sorry, 111. This is in base 2. You could also convert it to decimal if you wanted to. That also makes sense. So depending on the base you're in, you'll get a different answer, but the number will be the same. All right, so the bases that we tend to work with are hexadecimal, octal, binary, and decimal. Images we talked about. Basically, this is a bitmap. So there's a series of 1s and 0s, and if you look at where the 0s are, they form a shape, and that shape is, in this case, it looks like a little rocket thingy and a square over here. So this is a black and white bitmap. On the right here you have a grayscale bitmap where you have more values. Instead of just the 1 and the 0, you've got from 0 through to F. And depending on how far away you are from 0, you will have a slightly different shade of grey. Okay, and so this is more detailed, and you can imagine you can do a similar thing with color. You add more information or more storage per bit. We looked at audio, and basically the way to represent audio digitally is to sample it. And so if you sample it badly, you're going to get not a very good or accurate representation. If you sample it regularly and fast enough, then you're going to get a fairly good approximation of the actual sound, to the level where we probably can't tell the difference, right, if you have enough information. So that was lecture 2. There was a lot of process-based stuff in lecture 2, and as I said, it forms the basis of a lot of other things that we do later on in the course. So it's a really important lecture to get a handle on. Lecture 3 was combinatorial and digital logic. Digital logic, the gates operate on binary signals, have 1 or 2 values. Basically, there's some voltage. 0 to 2 volts is off or 0, 3 to 5 volts is on or 1, and then between 2 and 3 volts is an invalid state. So there's a shift between, or a switch over between on and off, and so there's a gap there. For our purposes, we don't really need to know too much about the electrical details. What we do need to know is that there is a 0 and a 1, and those are the only 2 cases you can have. There are 3 basic logic functions that can be applied to binary signals: and, or, and not. And you output true if all the outputs are true, or output true if any input is true, not output is the inverse of the input. So those are the basic rules. The way I tend to remember those, and, if you get a 0 anywhere, the output is 0. With or, if you get a 1 anywhere, the output is 1. Okay, and whatever works for you though, but I find that a convenient way to remember it. You can build more complex functions from those basic logic gates. Here are their symbols in the truth tables. So a truth table is basically a table that shows you all the possible inputs. In this case, there are 2 inputs, A and B, and then the output for those possible inputs based on the gate. Just a clarification there that A with a bar over it is the same as not A. So the bar means not or negation. The circle also means negation. So there's a couple of different ways to write that. Here are the other logic gates that we looked at: NAND, NOR, and XOR. And basically, NAND and NOR are the same as AND and OR, except they have a not after it, right? So they're the inverse of AND and OR. XOR is a little bit different, and it's the only truth table that has the 2 1s next to each other, like this over here. So that may be one way to remember it. XOR is 0110, for example. The other way to remember it is, look, when XOR has 2 values that are the same, you get a 0. When XOR has 2 values that are different, for A and B, you get a 1. Again, whichever way works for you to remember that. You'll also see that it looks a little bit like the OR symbol with an extra little line in front of it. Okay, that may be another way to remember it. So looking at the AND gate, how do we generate the truth table for this? Well, what are the possible inputs? A could be 0 and B could be 0. A could be 0 and B could be 1. A could be 1 and B could be 0, and A could be 1 and B could be 1. So with 2 inputs, you can only have 4 different states. It is imperative that you write them in this sequence. If you don't write them in this sequence, then it's not technically a correct truth table. All right, so let's have a look at the sequence here. This is actually just counting 0, 1, 2, and 3, correct? So if you have a bigger one with 8, for example, you would count from 0 through to 7. Okay, for AND, what did we say? Wherever there's a 0 on the input, there's a 0 on the output, right? So this one is 0, 0, 0. You can do that very quickly based on that rule. And then this one has no 0, so the answer is a 1. Okay. And you can do that for the other logic gates as well. So here is a more complicated circuit. What kind of gates does it have? It has, what's this one? This is XOR, and this one is NOR. It's got the little pointy kind of bit on the left. Okay, so we've got XOR and NOR. So my A and B could be 0, 0, 0, 1, 1, 0, 1, 1. That bit never changes, right? So if you want to memorize something, that's probably a useful thing to memorize. X is XOR, right? So we already looked at XOR. It's 0110. Now NOR. NOR is OR not. So let's just work out what OR is first. So what I tend to do with this is I'll tend to work out the base gate OR in this case, because it's just easier to work with, and it means I don't have to memorize so many things. So OR looks like this, right? 0111. So what does NOR, which is basically not X, what does that look like? 1000. So this one is, yep, and then obviously this is not part of my NOR table, so I'll cross that out. But basically it's easy to generate this from first principles. You can certainly memorize it if you want to, but there are a lot of things to memorize then if you take that path. We also looked at Boolean algebra, and the basic thing here was we wanted to get to these De Morgan's theorem. Basically, if you have an OR gate, you can turn it into an AND gate. If you have an AND gate, you can turn it into an OR gate. It's possible. You might have to do a little bit of manipulation with NOT gates to make that happen. And look at these pictures to show you how that works, the OR form and the AND form. But the basic idea here is I can convert OR gates into AND gates if I need to, and sometimes I need to. We moved on to a logic unit. So a logic unit has some logic gates on the left, and then this box, it's a multiplexer, which basically lets you choose one of the outputs from those gates on the left. So one time unit you might choose AND, the next time unit you might choose XOR, for example. To do that, you need, well, obviously the logic gates on the left and the A and B inputs to those, but you also need some selection lines, and those are the things that let you pick which ones you're actually going to allow through at this time unit. Selection logic looks like this. You'll see there's an S0, S1, S2, S3. These are from the decoder in this case, saying which ones to turn on. You'll see that there are 4 logic gates on the left. They're all AND gates, and for our purposes, we can view an AND gate as a blocker. It stops things from going through unless you turn it on. And in this case, you can only turn on one of them at a time through that S0, S1, S2, S3 input. On the right here, you'll see there are some OR gates, and for our purposes, we can think of OR gates as combiners. They allow things to flow through. So the AND gates block the signal unless it's the one you want, and the OR gates combine it back together so you have one output at the end. Decoder, its job is basically to take, in this case, 2 inputs and uncompress that to 4 outputs. If you had 3 inputs, you would have 8 outputs, 4, 16, and so on. So when we have a multiplexer, what we do is we have a decoder which takes some selection lines and uncompresses them, and then we have the selection logic which works out what to let through based on the value of the decoder. We also have the idea of a demultiplexer, and a demultiplexer is very similar in that you have, in this case, 1 input, and you can choose one of 4 possible outputs to turn on. And again, in this case, there's a decoder involved. A half adder was a piece of circuitry that we can use to simulate addition. Does it actually do addition? No, it doesn't know anything about the mathematical addition operator. It just combines things in a way that's useful for us. So for example, if I'm looking at adding 0 to 0, right, the answer is 0. If I add 0 and 1, the answer is 1. If I add 1 and 0, the answer is 1. If I add 1 and 1, the answer is 0 with a carry. So to translate that, if I take this one, if this is A and that's B and that's the sum, then A and B is 0, the sum is 0. A and B is 0, 1, the sum is 1. A and B is 1, 0, the sum is 1. A and B is 1, 1, the sum is 0 and the carry is 1, which means they'll be zeros normally because we haven't filled those in. And so again, we're using the circuits In this case, this is an XOR gate for the sum, and this is an AND gate for the carry. So you see how they work together. We're using those gates to give us the answers that we expect for that operation. Again, the environment doesn't know anything about the maths underneath it. It just knows you give me these signals, I'm going to give you this output. There is a full adder, which is basically two half adders. Same thing, they're just glued next to each other. And so what you'll see is you add, first of all, A and B together, and then if there's a carry in coming in as well, you can add that in the next stage. You do have to combine the carries, though, with a OR gate. Otherwise, you would have two carry outs. We also looked at subtraction, and basically the idea behind a subtraction circuit is that we want to reuse the full adder. So the full adder just does addition. We want to reuse it so that we can do subtraction with it as well. The way that works is we use the normal full adder, but we plug in an XOR gate here. That's the only difference. And we plug it in to the B part. And the reason we do the B part is if you write down A minus B, what we're actually going to be doing is A plus minus B. So we need to change B. And how do we change B? It has to be its negative equivalent. So do we have a process for that? We do. It's called 2's complement. Flip the bits and add 1. So what do you think this XOR gate is going to do? One of the two, right? It's either going to flip the bits or it's going to add 1. Yep. So in this case, it's going to flip the bits, actually. The other part up here is going to add the 1. So let's have a look at how it's going to flip the bits. S is a sign bit here, and it can be 0 or 1. If the sign bit is 0, we want to do addition. If the sign bit is 1, we want to do subtraction. If we're doing addition, do we want to change B? No, we want to leave it alone. It should be unchanged. So how do we achieve that? Well, if B is 0 and S is 0, and B is 1 when S is 0, what we would expect is when we XOR those two things together, we would get the same thing as B. If we don't, we have a problem. So 0 XOR 0 is 0. 0 XOR 1 is 1. Okay, looking at this, does B equal the XOR? Yes. Does B equal the XOR? So has B changed? No, it's gone through an XOR gate, but the output is the same as what B was. So is there any change? No. That's what we expect. We're doing addition. B must be unchanged. On the other case, when S is 1, which means we're doing subtraction, we want the opposite. Remember, we flip the bits. So when B is 0, B is 1 here, and S is 1, 1 XOR 0 is 1. When they're different, XOR is 1. When they're the same, XOR is 0. B was 0, now it's 1. Is it flipped? Cool. B was 1, now it's 0. Is it flipped? Yep. So just putting an XOR gate in here, because of the properties of XOR, allows us to flip the bits when we need to, when we want to do subtraction, and not flip the bits when we don't want to, when we're doing addition. It's actually a very simple change. That seems to be a complex thing we're achieving. All right. The other part, do you remember this sign bit here is a 0 or a 1? So when it's 0, you'll see it comes into here and it goes into the carry in of the full adder. So if you add in a 0, what do you get? Does it change the value? No. They have the same value. So for addition, that's fine. If we have a 1 here, we're adding a 1 once to this addition. Do you remember what the 2's complement process was? It was flip and add 1. So this is the XOR part, and this is the wire part, plugging into the carry in. Okay, so that's how we can achieve subtraction. It may be done differently in a normal circuit, for example, but this is a visual way to describe how you could achieve subtraction using a full adder. We then were able to build an arithmetic logic unit, and that's the same as a logic unit, except it now can do mathematical operations. So in this case, we've just added a full adder in, and you'll see it has its carry in, carry out, and so on as well. We looked at binary multiplication, and so for binary multiplication, what we did was we had some numbers like this, 1101 for example. Now this is the 1, the 2, the 4, the 8, 16, 32 and so on columns. I have 8 plus 4 is 12 plus 1 is 13. If I move these guys over one column and then I put a 0 in on the end here, this is a new 0. What have I got now? I've got 16 plus 8 is 24 plus 2 is 26. That's double the value I had before. Why is it double? Because I shifted to the left. And every time, each column is worth double its neighbor to the right. Yep. So if I move things that way, I'm going to double each value. So it's gone to 26. If I did it again, what's going to happen? I'm going to get 1, 1, 1, sorry, 1, 1, 0, 1, and then 2 zeros here, and this is a new 0. What value should this be? Double, it will be 52. So every time I shift left once, I double the value. Right? So it's an easy way to multiply by 2. On the other hand, if I'm doing division, and we worked out this was 26, right? 1, 2, 4, 8, 16. 16 plus 8, 24 plus 2 is 26. And if I go the other way, I move this one here, this one here, this one here, this one here, and that 0 falls off. What do I have now? 8 plus 4 plus 1 is 13. So this is dividing by 2. Just as easy. Not particularly useful, right? Because I probably want to divide by things that are not 2. Yeah? But just multiplying and dividing by 2 is actually really easy. It's done in a form of shifts, and you can shift left or you can shift right. If you shift left, you need to add in a 0 on the right hand side and you double the value. If you shift right, you need to drop something on the right and you halve the value. How this is achieved is through a shifter, and basically what it does is it's built so that you get stuff coming in and it goes one way if it's told to go that way, or it goes the other way if it's told to go the other way. There's some complications. If you're going this way, you should put a 0 on the end. If you're going this way, then if you've got negative numbers, you need to make sure that you put the sign bit back in properly. Right? Otherwise, a negative number might become a positive number, for example. That's not what you want. And then there's some control that says you can go left or right. Do you remember this shape down the bottom here? What kind of shape is this? This was our multiplexer that we saw before. Yep. And it has a 1 input for the selection. We moved on to arbitrary multiplication, and so let's do this again in decimal first. So 9 times 13 is 117. So 117 is okay, 64 plus 32 plus 16 plus 4 plus 1. So what have I done at the moment? Have I actually done binary multiplication? Not yet. I've just done the decimal version of it. That's great. I now have something to review or look at when I actually do the binary multiplication. The binary multiplication, it's done in terms of shifts. So you probably remember this diagram from the lecture on the multiplication. Basically, we have these powers of 2 here. You notice I'm using the powers of 2 now, not just 1, 2, 4, 8. And the reason is I need the powers of 2 because they're meaningful in this process. So this is the ones column, the 2 to the 0 column. And what it's saying is I've got this number 1001. This is 9 times 13, right? So 1001, if I want to multiply this one out, this is 9. There's a 1 in the ones column. So this is the power of 2. 2 to the 0, that means I shift it left 0 times. That's where that 0 comes in. So if I shift something left 0 times, what does it look like? The same as it looked like before. It hasn't changed, right? It's the original number. Then I've got a 0 in the 2 to the 1 column. So 9 shifted left once times, and this is where this 0 comes in. If I multiply anything by 0, I'm going to get 0. Then in this column, the 2 to the 2's column, I've got 1001 shifted left twice. There's a 1 here, so it happens once. And so when I shift something to the left twice, what happens? I put 2 zeros in on the right hand side, and then it's the original number, correct? It's moved left twice. What about the next one, 2 to the 3? Shifted left 3 times, there's a 1 there, so it happens once. That means there are 3 zeros and then 1001. Does that make sense? Now we have partial sums here. We're going to have to add them together. So if we add them together, let's do them in sequence. So we got 1001 plus 1001. What do we got here? 101101. So far so good? That's just adding these two together. Now we add this one. So what do we got? 3 zeros and then 1001. We add those two together and we get 1010. Carry the 1, 1, 1, 1. And there's an O on the front. And if you go back to the previous slide, 0110101, 0110101. So the way the arbitrary multiplication works is what you do is you find the powers of 2 in one of the numbers, pick the smaller one, right? It doesn't really matter, but do less work. And then you do some shifts based on the powers of 2 that there are. This one is, the first one is 0 shift, you do that once. This one is multiplied by 0, so there's no value at the end. This one is 2, so you do 2 shifts. This one is 3, you do 3 shifts. You add up the partial sums, and you're going to get your answer. Then we moved on to arbitrary division. And the way we did this was we did long division. So we had, for example, 26. So 26 will be, what's that, 24. Okay, 26. 11010. 4. Okay, so 26 divided by 4 is 6. This is 6, and the remainder is 2. So this is the reason I'm writing this at the top here, is so that I know when I'm going through this, there's going to be lots of ones and zeros on the page. I want to just confirm that I'm on the right track. So what am I dividing by? 4. What am I dividing into? 11010. And now I'm going to do the long division. And so first thing is 100, does it fit inside 1? No. Does it fit inside 11? No. So it will fit inside 110, correct? Yep. And so this is 110 is 6, right? 100 is 4. So how many times does it fit? It fits once. And I'll put the 1 above the last digit that I've been using, so there's a 1 there. And what's the remainder? 6 minus 4. 2. Remainder is 2. 100, does it fit inside 10? 4 into 2. Doesn't work, right? So I need to grab this one. Now I've got 5. 5 minus 4 is 1, and it fits once. Does 100 fit into 1? No. I grab the 0. Does 100 fit into 10? No. So it doesn't go at all, and we have something left over. So this is the answer, and this is the remainder. We cannot continue because there's not enough value to work with. So my answer is 110. Does that match my answer? Yep, 6. And the remainder is 2. I got what I expected. Now, technically, you can do this in 2's complement, do 2's complement subtractions. That's a lot of work. For the things that we're working with, they're pretty small, right? So this is 6 minus 4. You can work that out, probably even in your head, right? Okay, so that was arbitrary division. And so if you're doing an arbitrary division, you should probably work it out in decimal first, sort of have something confirm. Same thing with the multiplication, and that goes for a lot of these kinds of problems, by the way. If you have a way to do it in decimal first, try and do that to see what you're expecting to get, and then when you do the actual process, you can just verify that you're on the right track, because it's very, very easy to make mistakes. Okay, so that's the end of this section.